In this tutorial, we'll review the various tools we have for solving systems of equations, while recognizing the various ways that these tools can be used to solve puzzles and real-world problems. Example 1. This one's a little puzzle. The sum of two numbers is 11. 3 times the first number is 15 more than the second number. Find the numbers. So let's start by defining our variables. Now you may see this as a waste of time in your first few, but if you don't do this, you'll definitely lose points eventually, as you'll get mixed up in what your variable means along the way. It's easy to do, so I highly recommend that you define your variables at the beginning of your solution, like this. Let x equal the first number, and y equal the second number. Now, we read in our question that the sum of the two numbers is 11. So our equation would be x, our first number, plus y, our second number, has to equal 11. We have one equation down, but two unknowns, so we need another relationship. We're also told that 3 times the first number is 15 more than the second number. So 3x is 15 more, so we'll have to subtract 15 to get the second number, y. Or some would write it like this: 3x equals y plus 15. It's the exact same thing. The second number needs 15 more to be equal to 3 times the first number. Now, either equation is fine. Let's just go with the first. We now have two equations and two unknowns, so we're ready to solve, and we consider our solving options. We could graph it and identify the intersection point, and that is a great option for visualizing everything here. But if we just want the quickest way to a solution, an algebraic solution is usually best. So, thinking about our algebraic solution methods, substitution or elimination. Well, we see that the second equation is already solved for y. So substituting y from the second equation, or 3x minus 15, into the first equation. And we're ready to solve for x. Well, the brackets aren't doing anything, so let's remove those. And we can bring the x terms together. Let's add 15 to both sides. 4x equals 26. So we'll divide by 4, and we have x equals 6.5, or 6.5. Looking back at our let statement, and we see that we have x, or our first number. So we'll still need to solve for our second number, y. Plugging in 6.5 for x into our first equation, we can solve for y. So y equals 11 minus 6.5, or 4.5. Our overall solution is x, or our first number, is 6.5, and y, or our second number, is 4.5. Example 2. This one's more of a real-life problem. In this case, a fair has an admission fee of $1.50 for children and $4 for adults. On Saturday, 2,200 people entered the fair, and they made $5,050. So how many children and how many adults attended on that day? Let's define. Let C equal the number of children and A equal the number of adults. We're told that there were a total of 2,200 people that day. So C plus A would have to be $2,200. Also, we know that they made $5,050. The amount made from the children would be $1.50 per child times the number of children, which we said was C. And the amount made from adults would be $4 per adult times the number of adults, and we called that A. And the total amounts to $5,050. So we have two equations and two unknowns. Perfect. We're ready to solve. We take a look at it, and this one looks like a good one for either substitution or elimination. But let's work with substitution in this one. From the first equation, we can solve for either A or C. Let's choose A. Subtracting C from both sides, we have A equals 2,200 minus C. And then we substitute our A into the second equation, or 2,200 minus C into that second equation. And using distribution, 4 times 2,200 is 8,800, and 4 times negative C equals negative 4C. Bringing the C terms together, 1.5C minus 4C is negative 2.5C, and we subtract 8,800 from both sides, and now we divide by negative 2.5, and we get C equals 1,500. And we refer back, the number of children on that particular day was 1,500. And we still have to tell how many adults were there that day. So we need to go back and solve for A. Using our first equation and solving for A, we see that A equals 2,200 minus C, or plugging in our value for C, 2,200 minus 1,500, or 700. A equals 700, and that's the number of adults on that day. So we've solved it, and we've determined that on that day there were 1,500 children and 700 adults. In this tutorial, we looked at a couple of word problems involving systems of equations. One was more of a puzzle, while the other was more of a real-world problem. We have a nice set of tools for solving these. One, we could graph and identify the intersection of our graphs. And this is a great solution for visualizing, but a bit time-consuming. Two, we could involve algebra and our substitution strategy, and this is a very quick and efficient method. We could also solve using the elimination strategy, also algebraic. Sometimes we run into a nice opportunity to use elimination when it's not that easy to isolate the variable for substitution. Using these tools and staying organized allowed us to solve a nice variety of puzzles and real-world problems.